Welcome back to Discrete Math. I'm Dr. Jeff Groh. Today we're going to talk a little bit about number theory and cryptography. We begin our discussion with some words about divisibility and modular arithmetic. First, let me make a statement. 2 divides 6. What does that mean? If you divide 6 by 2, you get 3 with a remainder of 0. It goes evenly into 6, and in particular, 6 can be expressed as 3 times 2. So 2 goes evenly into a number if, when you divide, the remainder is 0. And so you get that number is 2 times some other number. So 10 is 5 times 2. So 2 divides 10. Also, 5 divides 10. We can even go further to say that 1 divides 10 and also 10 divides 10, because we could write this as 10 times 1. Hopefully, this discussion will motivate the following definition. We say that A divides B, where A and B are elements of the set of integers, if there exists K in the integers such that B is K times A. So 2 divides 6 if there's a constant K such that 6 is K times 2, for example. There's a very important notation that we are going to use. If A divides B, we write A divides B. We're going to use a vertical slash to represent the term divides. So, for example, 2 divides 6, or 5 divides 10. Here's a question for which you can easily see the answer. Does 2 divide 5? Obviously not. 5 would have to be equal to K times 2, where K is some integer. We know that K is not 2, because 2 times 2 is 4, not 5. And K is not 3, because 3 times 2 is 6. So there would have to be some number K, some integer K, between 2 and 3 in order to get K times 2 equals 5. But there are no integers between 2 and 3. So 2 does not divide 5. When we want to say that something does not divide something else, we use the vertical slash with a diagonal slash through the vertical slash. Now, let n and d be elements of the set of natural numbers. And by natural numbers, I'm assuming here 1, 2, 3, and so on. How many numbers, natural numbers, less than or equal to n are divisible by the number d? How can we determine this? Suppose m is such a number And let's suppose that D divides M. What does this statement mean? It means m is k times d for some k in the set of natural numbers. So let's start making a list. 1 times d, 2 times d, 3 times d, and so on, up to some number L times d, where we want that to be less than or equal to n. We'll let L be the maximum such. If that's the case, L is less than or equal to n divided by d. The inequality holds even if n is not divisible by d. So d doesn't divide n evenly. This might be some fraction. So the biggest L can get is the floor function of n divided by d. That will be the largest integer that you can possibly choose that's less than or equal to n over d, so that L times d is still smaller than or equal to n. So there's our answer. We need to learn a little bit more about how this divides operator works. So to that end, let a, b, and c be elements of the set of integers. And in particular, let's suppose that a is not 0. Then 1. If a divides b and a divides c, then a will divide b plus c. So if 2 divides 6 and 2 divides 10, then 2 divides 6 plus 10, or 16. And so that's fairly clear. Also, if a divides b, then a divides b times c. It already goes into b evenly, so it'll go into any multiple of b as well. Finally, if a divides b and b divides c, then a divides c. So there's a kind of transitive property with the divides operation. In our proof for number 1, we're going to assume that a divides b and a divides c. That means b is k1 times a and c is k2 times a. So let's look at b plus c. It's k1 times a plus k2 times a. Two terms with a factor of a. We can factor the a out. And k1 plus k2 must be an integer because the set of integers is closed under addition. Because this is an integer k, we deduce then that a divides b plus c. Keep in mind the definition of divides is a number is divisible by a if there's some constant k, so that a times k is that number. And so that's the end of the proof of part 1. Remember that these proofs almost always go back to the strict definition of the meanings of the terms that we're using. So a divides b, so b is k times a. Therefore, b times c, if you multiply both sides of this by c, will be c times k times a. But c times k is just another integer because of the closure of the set of integers under multiplication. And so bc is divisible by a. That's the end of the proof of part 2. Finally, for part c, a divides b means b is k1 times a. And b divided c means c is k2 times b. So does a divide c? Well, c will replace b with this k1a. We'll have k2, k1 times a. And we can, by the associative property of multiplication, associate these two. k1 times k2 is in fact an integer because of the closure law of multiplication for the set of integers. We deduce then, therefore, that A divides C, and that's the end of the proof. As a direct corollary, remember a corollary is a theorem that is a direct consequence of another theorem. Suppose A, B, and C are elements of the set of integers. A is not 0. If A divides B and A divides C, then A will also divide m times B plus n times C for any m and n that are in the set of integers. If A divides B in our proof, and A divides C, then B is k1 times A, and C is k2 times A, where the k's are integers. Also then, let's look at mb plus nc. B can be replaced by k1a, and C can be replaced by k2a. It follows then that we have mk1 plus nk2 times a, where this is just another integer k because of the closure laws of multiplication and addition over the set of integers. We deduce then that A divides mb plus nc. So any combination of b and c with integer coefficients will be divisible by A. Let's look at a very simple example. What's 5 divided by 2? Well, 2 goes into 5 twice, and there's a remainder of 1. You can see that 5 is 2 times 2 plus 1. 2 is the quotient, 1 is the remainder. N is the numerator, and 2 was the denominator. And it looks like in general that if I have numerator divided by denominator, I'll get the quotient plus the remainder divided by the denominator. That's usually how we do divisions. If you multiply everything in sight by d, you get n is d times the quotient plus the remainder. So this is a general formula that will always work when we're taking some numerator and dividing it by some denominator, where the numerator and denominator are integers and the denominator is not 0. This gives us something called the division algorithm. And basically it says this: if n is an integer and d is an element of the set of natural numbers, 1, 2, 3, and so on, then there exists unique integers q and r such that, first of all, we want r to be smaller than the denominator and bigger than 0, and that the numerator is the denominator times the quotient plus the remainder. In other words, the formula that we just wrote down a moment ago. The interesting part about this is the word unique. And so this will be an existence and uniqueness theorem that we need to prove. The division algorithm will often be denoted by TDA, and it should be noted that the division algorithm is not really an algorithm. There are names to all the parts of this division. Numerator divided by denominator is the quotient plus remainder divided by denominator. D is called the divisor. N is the dividend. Q is, of course, the quotient, and R is, of course, the remainder. We're also going to introduce some notation. Let us have n equals dq plus r, where n, dq, and r all come from the appropriate ranges. We'll assume that r is a natural number or 0, and d also a natural number. Then q will be denoted by n d. So q is the number of times that d goes evenly into n. Also, r will be in mod d. So the modulo is this word. And we usually just abbreviate it by saying mod. So in mod d will be the remainder, in div d will be the quotient for this division algorithm. Let's look at the following. 25 div 8. We're asking how many times does 8 go into 25, and the answer is, of course, 3. But 25 mod 8 would be the remainder when you do the division of 25 divided by 8. 8 divided into 25. And the remainder is 1. Because 3 times 8 is 24, you'll have a remainder of 1. In our next example, it might be a little surprising if we start throwing in negative numbers. But the answer should come from the division algorithm. We want negative 11 to be 3 times some quotient plus some remainder, where again the remainder must be less than the divisor, in this case 3. So, which integers will satisfy this bill? To get something negative, where r is positive, q has to be negative in this process. But what negative number will work? If you use something like negative 3, 3 times negative 3 will be negative 9, but then r would have to be negative, and that's not allowed. So if q is equal to negative 4, 3 times negative 4 is negative 12, you'll add plus 1. So negative 11 is 3 times negative 4 plus 1. So q, the quotient, is negative 4, and r, the remainder, is positive 1. From this we deduce then that negative 11 div 3 is negative 4, and negative 11 mod 3 is positive 1. It's usually pretty easy to figure out what negative 11 mod whatever will be. All you do is you keep adding the modulus to these negative numbers until you get something positive. The first time you get something positive, or 0, that will be the remainder. I have to caution, many programming languages produce something different. In mod k, when n is negative. In positive, they usually produce the right thing. In negative, sometimes they give something a little bit different. We give, in mod k, is n minus a certain number of multiples of n divided by k, the floor function. How many times does k go into n? That's your quotient, quotient times your divisor. And we're subtracting that from n. Some languages give n mod k is instead n minus d times the ceiling function of n over k. I wanted to give you an introduction to something called modular arithmetic. And in particular, ultimately, I want to describe something called z sub p, where p is some natural number. Let's look at a specific example, z2. z2 has only two numbers, 0 and 1. The addition table well, 0 added to anything is itself. The addition table requires closure under addition in this set. 1 plus 1 is normally 2, but in Z2 you subtract 2's until you get back within this set. So in Z2, 1 plus 1 is 0. The multiplication is trivial in Z2. If you multiply anything by 0, you get 0, and 1 times 1 is 1. Let's look at Z3. Z3 only has three numbers, 0, 1, and 2. We're again going to perform the operations so that if we end up with an addition or a multiplication problem that is outside of this set, then we'll add or subtract 3 until we're back within that set. So in our addition table, if you add 0 to anything, it leaves it alone. 1 plus 1 is 2 in Z3. 1 plus 2 would normally be 3. 3 is not in this set, so we have to subtract 3 to get ourselves back in. So 1 plus 2 is 0. 2 plus 1 is 0. How about 2 plus 2? Normally that would be 4, but we're no longer in the set, so we have to subtract 3 to get back within the set. And that gives 1. 2 plus 2 is 1 in the set Z3. Now what about the multiplication table? If you multiply anything by 0, you get 0. If you multiply anything by 1, you get itself. 2 times 2 is normally 4. It's not in the set. So we have to subtract 3 to get back within the set. And therefore 2 times 2 is 1 in the set Z3. Notice that in Z3, when we calculate 2 times 2, we do that mod 3. 2 times 2 is 4. Subtract 3, that gives you 1. In other words, we're doing modular arithmetic when we're dealing with ZP for some P. 2 plus 2 is 4. Mod 3, that's 1. Here's another definition and some notation. We say that A is congruent to B mod or modulo M if M divides the difference, if M goes evenly into it. For the notation, we write A is congruent to B mod M. Let's give some quick examples. 10 is congruent to 1 mod 3. You can subtract 3 3's, making it equal to 1. But there are other numbers congruent to 1 mod 3. 7 is congruent to 1 mod 3. 4 is congruent to 1 mod 3. And, of course, 1 is congruent to 1 mod 3. We can also say 7 is congruent to 4 mod 3. Technically, to test for congruence, we need to see if 3 divides 10 minus 1. Well, 10 minus 1 is 9. 3 divides 9 because 9 is 3 times 3. And so that means that 10 will be congruent to 1 mod 3 by the definition given. In our next theorem, we're going to let a and b be elements of the set of integers and m be an element of the set of natural numbers. Then a is congruent to b mod m if and only if a mod m gives you the same thing as b mod m. So in our proof, suppose a is congruent to b mod m. Well, what does that mean? It means m divides a minus b, so that a minus b is k times m for some k in the set of integers. Now, let a mod m be R1 and b mod m be R2, where R1 and R2, these R sub i's, will be bigger than or equal to 0, but less than m. What do these two equations mean? They mean that a is k1 times m plus r1, and also b is k1 times n plus r2, where k1 and k2 are integers. Now let's plug these things back up into here. A minus b, that's going to be k1m plus r1 minus k2m plus r2 equals k times m. And let's see what happens when we rearrange these numbers. If we rearrange these numbers, putting all the terms involving m on one side, we'll have r1 minus r2 is equal to km minus k1m, and then when this negative comes over, it'll be plus k2m. So in other words, r1 minus r2 must in fact be an integer multiple of m. But remember, r1 and r2 have to be smaller than m. And so when you subtract them, you must get something between and not including negative m to m, which means the only possibility for this integer is 0, which means then that r1 equals r2. That gives us a mod m equals b mod m. Since all of the steps are reversible, we get equivalence. Is 17 congruent to 5 mod 6? Well, just keep subtracting 6's until you get it down to whatever the minimum number is. 17 minus 6 would be 11. 11 minus 6 is 5. So yes. The answer is yes, but we could answer this a little more definitively. The question might be phrased as, does 6 divide 17 minus 5? And this is the same thing, does 6 divide 12? And the answer there is, yeah, 12 is 2 times 6, so that 6 divides the difference, and then therefore 17 will be congruent to 5 mod 6. Is 24 congruent to 14 mod 6? The answer here is obviously no. 24 minus 14 is 10, and 6 does not divide evenly into 10. And so, no. Let's just lay this out there in terms of a theorem, if a and b are integers and m is a natural number, then a is congruent to b mod m if and only if there exists an integer k such that a minus b is equal to k times m. In other words, a is b plus k times m for some integer k. The proof is very straightforward. We said a is congruent to b mod m if and only if m divides a minus b. That's equivalent to a minus b is k times m for some integer k, and that easily reduces to this formula here. Remember that 17 is congruent to 11 mod 6, but it's also congruent to 5 mod 6. It's also congruent to 23 mod 6. You could be adding things as well as subtracting. It's congruent to negative 1 mod 6. You can go negative. We're going to make a definition. The set of all numbers n in the set of integers such that n is congruent to a mod m is called the congruence class. RU of A. The congruence class, everything congruent to A mod m, is its congruence class. So let's look at an example. 0 mod 3 has congruence class of it's infinite and goes both ways, positive, negative, and includes 0 in this case. What about 1 mod 3? What is its congruence class? Well, you'll add 1 to these basically. Clearly 4 is congruent to 1 mod 3. You subtract 3 from 4, you get 1. And all these others, they're always 3 units apart, as you can see. What about 4 mod 5? We'll have 4. If we subtract 5, we'll get negative 1. Subtract 5, you get negative 6. If you add 5, you'll get 9. If you add 5 again, you get 14, and so on. So this will be the congruence class of 4 mod 5. This modular arithmetic may seem a little different than usual arithmetic, but it satisfies some of the same rules. Then if A is congruent to B mod m and C is congruent to D mod m, then A plus C will be congruent to B plus D mod m. In addition, A times C will be congruent to B times D mod m. So this modular arithmetic maintains this congruence over addition and multiplication. To prove this, we need to write down what we mean by some of these statements. A is congruent to B mod m means m divides A minus B. And C is congruent to D mod m means m divides C minus D. By a theorem we've already proved, it follows then that m divides the sum A minus B plus c minus d. But we can rearrange this as m divides a plus c minus b plus d. And that's precisely what it means for a plus c to be congruent to b plus d, mod m, is that m divides the difference. So how do we prove the congruence of these products? Well, let's just go back and see what these actually mean again. A minus b is k1 times m for some integer k1, and c minus d is k2 times m for some integer k2. So a is b plus k1m, and c is d plus k2m. It follows then that a times c is b plus k1m times d plus k2m. Well, that's b times d. And then we'll have b times k2m plus d times k1m plus k1, k2, m squared. It follows then that b times d will have added to it a multiple of m, b k2 plus d k1 plus k1, k2, m. But that's what it means for AC to be congruent to BD. And so the theorem is over. In the modular arithmetic for z sub n is called the base. So in particular, 7 is congruent to 2 mod 5. The base that we're working in is 5. Similarly, 11 is congruent to 1 mod 5. Let's check our rules from the last theorem. If we add these, is it true that 18 is congruent to 3 mod 5? Well, you can subtract multiples of 5 from 18 to get the congruence class. And clearly 3 times 5 is 15, subtracted from 18 gives you 3. And so 18 is in fact congruent to 3 mod 5. What about the product? Is it true that 77 is congruent to 2 mod 5? Well, 5 times 15 is 75. That'll leave a remainder of 2. So 77 is in fact congruent to 2 mod 5. There are certain things you cannot do with modular arithmetic, and in particular, the cancellation principle is false for modular arithmetic. Normally, if we have a times b equals a times c, that implies you can cancel a off and get b equals c. However, if you have a times b is congruent to a times c, mod m, that will not necessarily imply that b is congruent to c, mod m. To see this, let's look at an example. To see this, note that 4 times 3 is congruent to 3 times 3 mod 3. 4 times 3 is 12, that's congruent to 0. And 3 times 3 is 9, which is also congruent to 0. But you cannot cancel the 3 off. 4 is not congruent to 3 mod 3. So you cannot cancel common factors off. This process doesn't work. You don't cancel common factors off. It doesn't lead to good results. So while you can multiply both sides by a common factor in a congruence, you can't cancel stuff off. So the cancellation principle is false. Also, the law of exponents may not work either. A is congruent to B, mod M, and C is congruent to D, mod M, then we may not have A to the C congruent to B to the D, mod M. This may be false. So let's do an example. It only takes one counterexample to show that something is false. For example, 6 is congruent to 2 mod 4, and 4 is congruent to 0 mod 4. So the question we have is 6 to the power 4 congruent to 2 to the power 0, which is 1 mod 4. Well, 6 to the power 4 is 1296, which, by the way, is 324 times 4, which means that 6 to the 4 is congruent to 0 mod 4, because 4 goes evenly into 1296 with no remainder. The remainder is 0, so it's congruent to 0, not 1 mod 4. So this would be an example where you can't exponentiate both sides, even though you get these two congruences. There are closure laws for congruences. For example, A plus B mod M will be congruent to the following: A mod M plus B mod M, and then mod M. So you take the modulo M of all of this. Similarly, A times B mod M will be congruent to A mod M times B mod M, and then mod M. Let's find the value of 19 cubed mod 31 to the power of 4 mod 23. So we'll calculate this and then take it modulo 23. To do this, I first need to calculate 19 cubed. And so I'll get 6859 mod 31. So how do I take 6859 mod 31? Well, I divide by 31 and see what the remainder is. And so I get 8 mod 31. 8 is the remainder when I divide 6859 by 31. So 8 to the power 4 is 4096, but now it's mod 23. So I have to divide 4096 by 23 and see what the remainder is. So if I divide 4096 by 23, subtract the integer part, which is 178, and then multiply back 23, I'll get the remainder, which is 2 mod 23. I should illustrate some of this for you. 4096, how many times does 23 go into there? Well, it goes into 40 once, with a remainder of 17. How many times does 23 go into 179? Well, the answer is 70. 7 times. That's 140 plus 161. That's going to have a remainder of 18. And so that's going to be 8. 160 plus 24 is 184. If we subtract, we get a remainder of 2. and so we get 2 mod 23. This might be an unusual way of dividing that you may have not seen before, but it does help you learn how to do these divisions faster than the usual algorithm that you may have seen in the past. Considering Zn, we have a little notation that we're going to introduce. When we say A plus B in the set Zn, we're going to put a little n here. And so that means A plus B mod n. We're going to do the sum modulo n. Also, A times B, we'll put a little subscript of n indicating that we're doing it with the arithmetic for Zn. This will be A times B mod n. So for example, if I have 7 plus base 11, 9, that's going to be 7 plus 9 modulo 11. Well, 7 plus 9 is 16. And we'll subtract 11. That gives us 5 mod 11. And so we'll say 7 plus on base 11, 9 is 5. 7 plus 9 is 5 when we're in Z11. Let me introduce you to a few more abstract concepts. What is a group? It's a set G together with a binary operation. Binary means you plug two things in, it outputs one thing, kind of like addition is a binary operation. So is multiplication a binary operation. We're going to call this binary operation circle plus. It takes two things in, so G cross G is a set of ordered pairs of things coming from the set G, and it will output something in G. So a group is a set together with a binary operation that satisfies the following properties. Just for emphasis, I'm going to give you the 0th property of a group. It's called the closure law. It's kind of implied by something that we've already written here. The closure law says that when you add two things in the group using circle plus, you get something in the group. Right. So if A and B are elements of G, then A circle plus B is also an element of G. Well, duh. The second property is the associative law. It's very unusual when things don't satisfy the associative law, but that's A circle plus B circle plus C gives you the same thing as A circle plus B circle plus C. So it doesn't matter how you associate this plus. There's two more properties. The second property will be the existence of an identity. For addition, the identity is often denoted by 0, but we're going to denote it by E. So A circle plus E will always be equal to E circle plus A, which is A. If you add something to the additive identity, it leaves it alone. Finally, existence of inverses. And in particular, we're thinking about additive inverses here. So for any A, there will exist a B, so that when you add them together, you get the identity, 0. Normally we denote these by, instead of B, we'll write negative A, because A circle plus negative A will give you the 0. adding to this, if G together with its addition is a group, and it satisfies the commutative law, we call G an abelian group. Or a commutative group. We call it abelian because of the famous mathematician Abel. We can do a lot of weird things with groups. First of all, note that Zn is a group under the operation n plus for any natural number n. So yes, it will be associative. In fact, it won't just be any group, it'll be an abelian group because of the commutativity of addition under the modular arithmetic. But let me give you another example. Suppose I let my group G be the set of positive real numbers, and we'll define my circle plus to be multiplication. So notice that 0 is not an element of R plus, but that's okay. First of all, I have to check that this set together with this operation satisfies those four properties for a group. One of those is kind of obvious and a lot of people omit it, namely the closure law. Well, we get closure here. If you multiply two positive numbers, because addition is multiplication, by definition, according to this rule, then that will be an element of R plus if A and B are, so that we get closure. Multiplication is associative, so the associative law works. What about the existence of an identity? What's the identity here so that you get A? And the answer is, if your addition is multiplication, then the identity E had better be 1. So in this case, the identity is 1, not 0, because my addition has been defined to be multiplication. What about additive inverses? A times whatever the inverse is, we'll say B, equals my identity, which is 1. But A plus B, circle plus B, is A times B, which means B has to be 1 divided by A. If A is a positive real number, then 1 over A is also a positive real number. And so the additive inverse here is the multiplicative inverse under the usual multiplication. So as you can see, we can do a lot of very strange abstract things here, where I'm forcing you to think about the details. So there are a large number of examples of groups. For instance, if I have invertible matrices that have a determinant that's not 0, those form a group where the group operation is matrix multiplication. The set of all invertible matrices under the group operation of matrix multiplication is called the general linear group. If you're dealing with the set of invertible matrices having a determinant equal to positive 1, those form something called the special orthogonal group. Next, I want to define what I mean by a ring. It's a set R together with two operations, plus and times. These are both binary operations. where R together with plus is an abelian group. So with plus you get an abelian group, and times is closed. It satisfies an associative law, but we don't necessarily assume that it satisfies a commutative law for multiplication. If it is commutative, we call it an abelian ring. But we do assume one more thing, and a distributive law. Now, if you have two operations, you kind of have to explain how those operations work in conjunction with each other. So if I have A times B plus C, that has to give me A times B plus A times C. So you can distribute one factor to each term, just as you could normally in our regular algebraic rules. So what are we not assuming here? We're not assuming that the multiplication is commutative. We're not assuming that there is anything like a 1, a number 1 for a ring. And we're not assuming that ring elements have multiplicative inverses. So let me give you an example of a ring. Z3 is a ring. Let's look at the multiplication table in particular. Remember, Z3 only has numbers 0, 1, and 2. 0 times anything is 0. 1 times anything is itself. 2 times 2 is 1 under the modular arithmetic. So notice that 2 times 2 is 1. Normally, 2 times its multiplicative inverse is 1. So in this case, 1/2 will be the same as 2 in this modular arithmetic. Technically, I shouldn't write it as 1/2. I should write it as the multiplicative inverse of 2 is 2. In this case, you can see that 2 has a multiplicative inverse because you can have 2 times something equals 1. 1 is, of course, its own multiplicative inverse, and there is no multiplicative inverse for 0. Now let's look at a different group. Let's consider Z4, and in particular its multiplication table. Zero times anything is 0. 1 times anything is itself. 2 times 2 in Z4 is 0. 2 times 3 would be 6. Subtract 4. You get 2. Same thing with 3 times 2. 3 times 3 would be 9. Subtract 4. That's 5. Subtract another 4. That's 1. So 3 times 3 is 1 in Z4. So you can see that 3 times 3 is 1, so the multiplicative inverse of 3 is 3. But 1 is, of course, its own multiplicative inverse. There is no multiplicative inverse for 2. Because there's nothing in Z4 that you can multiply it by that gives you 1. So, in other words, multiplicative inverses in Z4 don't exist. In fact, it's possible to have 2 times 2 equal 0 in Z4. This is very unusual because this means that you have trouble solving equations in Z4 using the usual rules of arithmetic, because this kind of scenario will always happen if the number here is not a prime. So if I'm looking at Z6, 2 times 3 is 0. So again, I get this weird situation where I have two non-zero numbers multiplied together equaling 0. In addition, you can show that both 2 inverse and 3 inverse do not exist in Z6. Anytime you have a proper divisor of the base, you end up with no inverse to that number, besides, of course, 1.